Good morning, everyone. Can you hear me? That's always the first question. So let me know through the audio. Can you turn on your mic? I read yes. So, welcome to the second lecture, my second lecture, your fifth lecture, I think, already on this course. So, before we start, I want to remind you that you can feel free to interrupt me during the lecture if you have any questions. I would really like the dialogue in this lecture, so feel free to turn on your mic and just give me some feedback. It's also for these questions when I ask, can you hear me? It's good to have some audio feedback from you, so I know you. I don't have to read the chat, which I try to do, but it's a bit harder to see on my computer screen. Is that okay for you? So now's the time to turn on the mic and say, yeah, it's good.
Yeah, it's good.
Yeah, cool. Yeah. Thanks. Okay, so I'm experimenting with different layouts. So today I've got a totally new layout in store for you, and we'll see what works. It's also some creative process for me to see what is possible and what I like. So today we're going into the null hypothesis testing a bit further. Last week we started with Conrad, with throwing the coin and determining if Conrad is in balance or not, and actually to see how we get from a sample distribution to a sampling distribution. I asked you all to throw the coin 10 times and determine what actually the sampling distribution looked like under a certain assumption. It's the assumption that the null would be true. So we tested that, and we touched upon making decisions about the reasoning within statistics. And today we are going to thoroughly expand on that, and I hope at the end of this lecture you would have a thorough understanding of the null hypothesis testing. We're going to relate that to this binomial distribution that we started with last week. So these are the topics for today. The slides are already online, so you can follow along there if you wish. So, the null hypothesis testing, significance testing, we're focusing specifically on one area of the null hypothesis testing, and the specific area is the Neyman-Pearson paradigm. They were not the first to think of hypothesis testing, of course. This goes way back, but in the same era, they had a colleague called Ronald Fisher, and Ronald Fisher he also had a notion on doing statistics, and he had a thorough basis of the null testing. But what Ronald Fisher suggested was that the p-value as you would obtain it would indicate a level of, let's say, effect size. He would say that the lower the p-value is, the more effect there is, and if the p-value is higher, then there would be less effect. So Fisher, Fisher had a sort of scaled measure that he attributed to the value of the p-value, which indicated some form of effect. And what Neyman and Pearson did is that they coupled the null hypothesis testing to reasoning. So that means that Neyman and Fisher transformed this gliding scale of let's say confidence in the thing that you find, essentially the rarity of your findings, and they aligned it with reasoning. And when we talk about reasoning, it's more about decision making. So in line what Roland has already taught you is that if it's decision making, it's making a conclusion, and the conclusions are based on premises. So they combine these two to have a notion on what the premises are and what the conclusion is that you make based on your findings. So we'll go through that process today. So to start, we will start again, of course, with the null hypothesis. What it is again, we touched upon this, and I'm sure you already understand. It's the skeptical point of view. It's the assumption that there is no effect, that there's no preference, and all these things that a skeptical viewpoint would take on any assumption that you have on alternative hypothesis that you could think of. And the reason I put it up here is because I understand that you probably are familiar with this notion, but what I would like to see happen along the way of this course is that this attribute of the null hypothesis, of being skeptical, of assuming nothing to be true, would be a more integral part of your personality. So I told you earlier that we hope to change you as a human being in this course. So one of the things is this. So instead of having all kinds of ideas on how the results of research will be, and striving to find that, it might be better to have a more skeptical viewpoint. Also, not just on the research of others, but also on your own research and your own ideas. And I think that Roland already showed you in his lecture I think he had the slide where different researchers were provided the same data and were asked to analyze the data and to report on it. And what he showed was that there were varying results on these same data, and the conclusions therefore would also differ wildly. So it's also the preconception of researchers which can affect the outcome of your research. So to have a thorough self-reflection, so to say, where you doubt your own conclusions and be mindful of that, I think would be the better way to go. And I think that you in particular, as you study psychology, are more equipped than other researchers to arm yourself for this bias, because you know within from your studies in psychology, we humans have all kinds of bias. There's a recency effect, there's a halo effect, there's all kinds of effects that bias our view on reality. And as you know this, then you can arm yourself for these kinds of biases. Does that make sense? So it's time again to give me some feedback. So I don't.
Yes.
Yeah. Okay. Cool.
Sharon, can I interrupt for a second?
Oh, of course.
In the YouTube live stream, there's a constant bell ringing. It's a little bit annoying.
I think it's the bell when students come into the Zoom session. And I hope it's over. I hope everybody is in now, and I'll see if I can turn that off for next recording.
Okay.
Yeah. So the alternative hypothesis is then, of course, the hypothesis where you refute your skepticism, where you think, well, there might be an effect in a certain direction, or you might not even have an idea on the direction of your of the effect. So if we look again to last lecture, where, and also Roland touched upon this, where we have the empirical cycle, we go through this deduction and induction phase, and we have to specify our alternative hypothesis, and this is the part where we determine what the hypothesis is, and we have to formalize it a bit more in the Neyman-Pearson paradigm, and that's what we'll be doing today. I also heard from the tutors that the last week's lecture left a lot of you still a bit in the dark, and I know that is the case. It's planting the seeds for this lecture to build upon, and not just this lecture, but the entire course will build on the stuff that we talked about in the first and second lecture. And so what we do, especially within the Neyman-Pearson paradigm, is use the frequentist statistics, use the frequentist probabilities as the basis to determine the null hypothesis testing. So it's an objective probability, and it's based on the relative frequency in the long run. So do you have any idea if it's also possible to have objective, a subjective probability? Anyone?
Yeah.
Very good. And what would that entail?
Well, subjective always includes I'm not sure whether a certain bias is the correct formulation, but if I want to look for an effect, I might have a sample not determined by the average, but I don't know, more specific, and then my results that I find are more subjective.
Okay, but in that case, you would still say it's based on data, right? But also for anyone else, just chip in and then feel free to help and to tell us your thoughts on this, because one point that you made is you said your belief on something. So if you're talking about subjective probability, then do you think that there are any people working on subjective probability?
I was thinking something, but like it's not really based on anything that I've read so far. But I think something that would maybe be subjective probability is when you just make your own conclusion based on facts that are out there. Like, for example, at the moment there's like the NBA playoffs are happening, and people saying that a certain outcome is gonna happen based on things that have happened in the regular season might be like, so there would be a probability of winning, but somebody else might think something else based on that same data.
Yeah.
Maybe that's subjective probability.
Sure. But you say that it's still based on the data in the things that happened in the past. So when so what you're saying is correct in the sense that it's your thought, your opinion on what a probable outcome would be. But what you're both are doing, and that's totally fine, but you're both relating that to not just data, but also to, for example, the NBA example at the playoffs, on previous results. But if you're really talking about subjective probability, then it's absolutely subjective. It could be my opinion, my thoughts. What is the probability? What is the probability I think that it will rain today or tomorrow? And I could say, well, I think the sun is shining. Yeah. Today, no, it's not going to rain today. So I think the probability of it's going to rain today is probably very low, like say 5%. But I can update my probability if I see a dark clouds coming over. I could update my probability, and it would still be subjective. I'm not relating it to the relative frequency on the long run. I'm not looking at what was the amount of rain that has fallen on this day in the previous whatever years. No, it's pure subjective. So there is also a subjective viewpoint on probability, and the question I asked you also was, are there people that work primarily with subjective probabilities? And I see in the chat that Evelyn is saying, isn't that what the Bayesians do? And that's absolutely correct. So the Bayesians have a subjective view on probability. And during this course, we will also transition into the Bayesian viewpoint, because the frequentist approach works very well, but it has its flaws. And during this course we'll see what these flaws are, and we will also dive into this subjective probability based on Bayesian theorem to see where Bayes could help in finding answers to hypotheses that we have. So very good point. Okay. So the frequencies probability. So before I'm going to dive into the Neyman Pearson paradigm. It's good to have a bit of a notion again on what we can do, what it means, the relative frequency on the long run, and what this objective probability not just entails, but what it results that in what the things that we can do with it. So one of the main workhorses for objective probability and relative frequency in the long run is that we can determine, based on a sample average, what the confidence interval is within such a sample. You've had this before in year one, and the confidence interval, as I've defined here, is the 95 confidence interval, which, based on this formula, and just you don't have to know this formula by heart, but try to look at it for a second and see that it's defined by the standard deviation divided by the square root of n, where n is the sample size. And if you then, based on that standard error, want to determine the upper and the lower bound, then you have to subtract that from the average, multiply it by 1.96, and then you will get a confidence interval. But one of the things to notice is that if you divide by the square root of n, and assume, for example, that the standard deviation would stay the same, that would mean that if you increase the sample size, then your confidence interval will shrink. And if we look at that in the next slide, for example, I have here, for example, a test between two groups, and I have two means. That's the height of the bars, which you can find here, and we have the confidence interval. So would you assume that there would be a significant difference between these two groups? What are your thoughts on these? Let me know. Would there be a significant difference? Anyone?
I'd say because the sample sizes are so small, there could be significant differences.
Anyone agrees? Is there anyone that disagrees? So take a look at this, at these error bars. We see the upper bound and we see the lower bound of these error bars. So would you expect there to be a significant difference if you look at these error bars? Anyone?
I would say no, because they overlap.
Exactly. The intervals overlap. So that means that in 95% of the relative frequency in the long run, if we replicate this experiment in the long run, then in 95% of the time, the average, the population average, would be within the upper and lower bound of the confidence intervals. So I'm 95% sure that it would fall in between the lower and the upper bounds. That's for the one group and the other, and there's overlap. So there's going to be overlap. That's the assumption based on these confidence intervals. Is that clear? Yeah. So now, what happens if we increase the sample size? We say, well, we have a lot of people. We're going to test, and we're going to test with more people. And now, we will probably have a significance difference, right? Agree?
Yes.
So, let's look, for example, to the difference in intelligence between men and women. By the way, do you think that there's a difference in intelligence for men and women? No? I see. Absolutely. Lucy says, I like reading the chat, but I like it more if people just talk to me, so feel free to turn on your mic. I see a lot of no's. Women are more educated on average.
I think in the first year we talked about how on many intelligence tests men score higher because most items are from specific subjects that are more catered to men.
Mm-hmm. So, in replicated studies, it is found that there is a difference in intelligence, but it's a difference of 1 point. And do you guys know what the average intelligence is, by the way?
100.
Yeah, exactly. So the difference that is found is an average intelligence for one group 100 and for the other 101, for example. But do you also know what the standard deviation is for intelligence?
15.
It's 15, yeah. So if you know that the standard deviation is 15, then a difference of 1 is not relevant, right? That makes sense, right?
Yes.
So the problem now is that if you just add more and more participants, your standard errors will just keep on shrinking. They will become smaller and smaller and smaller, and at one point you will find significant differences, even if you have very small effect sizes. So that means that we have to be cautious to base on our conclusions only on the result of the p-value, because it only says that it's significant and that will result in a conclusion. but it doesn't mean that the amount of effect that is found is actually relevant. So we have to realize that it's just not enough to just report the fact that it's a significant value. So, and we will go into this in more detail during this course. I see if it could also be stereotype threat. It's not the main point of the discussion at this point. So I want to relate it to just the fact that you get a notion that if you just keep on increasing the sample size, you will find a significant difference eventually. And Roland touched upon this, I think also already a bit, that this is actually a problem, right? So if you have your hypothesis and you do your analysis and there's no significant difference, and just add another participant or two, and then I'll find it, and I'll be a happy camper.
Quick question, sorry.
Yeah.
So how does it correlate? Because someone said earlier on that because it was such a small sample size, you can detect faster, smaller effects, and with a larger sample size, you detect bigger effects faster. Or how does that correlate with each other again?
Yeah, we'll go into this, and I hope that at the end of this lecture you will have a more thorough notion on that point, because expanding the sample size will actually allow you to find small effects. So if there are just small effects, you really need to have a lot of participants to even find it, if it's really something that is out there. But we'll go into this. Okay. So this notion of the relative frequency in the long run, I want to touch upon this a little bit more, and relate this to the confidence interval, because we talked about this confidence interval and said that we know that if you choose a confidence interval of 95%, that you're sure that the population mean would fall between the confidence interval in 95% of the time. So I would like to visualize this a bit more. So what I've done here is I have a population, some population, whatever, that is normally distributed, and we have a population mean, a mu, that you will find right in the center here. So what you see here is that from this population, I have sampled, I've pulled a sample, but I've done that 100 times. So the gray bars here, let's see if I can zoom in if this works. Yeah, this works. The gray bars, the horizontal bars, represent one sample with a lower bound and an upper bound. And what we see is that for this first sample that I took, the population mean, this one, falls between the lower bound and the upper bound. And for the second sample, again, it falls between the lower bound and the upper bound. And for all these gray bars, which are just a random sample from this population, the notion, it holds that the population mean falls between the upper bound and the lower bound, except for this red one. For this red one, the population mean is outside of the confidence intervals. And for the rest, it still holds, and here again we see that it doesn't hold for these two, and also not here, and also not here. But out of 100, 95 95 from these samples, the population mean falls between the upper bound and the lower bound. But what you also see, and well, you have to look closely, is that the confidence interval, they're not the same. Do you see that? Some are a bit wider, some are a bit smaller. So because the confidence interval depend on the specific sample that you took, on those properties, so they could be more spread out or they could be at random more close together. If you calculate these confidence intervals, they will vary per sample. So we have to think about what that means for the interpretation and for the definition of the confidence interval, because a lot of researchers, when asked what does the 95 confidence interval mean, will say that the 95% confidence interval would mean that the population mean falls between, so you're certain for 95% that your population mean falls between the lower bound and the upper bound of this confidence interval. And that is actually not correct. Is there anyone who can elaborate why that wouldn't be correct? If I say that I'm 95% certain that the population mean would fall between this confidence interval.
Because the confidence intervals vary based on what sample you have. So it's not that it will fall between those confident or those, what do you call them?
Lower bound and upper bound?
Low bounds and upper bounds, but it's that if you were to repeat the experiments,
Yeah.
or there would be a 95%, or in 95% of the cases, it would fall between the lower bound and upper bound of those respective experiments.
Yeah. So that's a very good point. And so the key here is that the word "this" refers to the specific value of the lower bound and the upper bound. But it's not about the specific value. It's about, exactly as you say, about the replication. So if we're talking about the relative frequency on the long run, it means that we replicate this study again and again. And if we would have done that, then in 95% of the times, the population mean would be between the upper and the lower bounds, but not this specific lower bound. So that's a nuance, but it relates to the fact that we're talking about the relative frequency on the long run. So maybe during this course we'll have the debate between the Bayesians, Erik-Jan Wagemaker and Danny Borsboom as a frequentist, and they will discuss this debate. But Erik-Jan might ask you the definition or the what you think that is the meaning of the 95 confidence interval, and then you have to be mindful. And sometimes he puts out money, but I'm not sure how this will work in Corona time. But okay, he'll send you a ticky. Lower bound. So there's a question: when you do, then why do we calculate the upper and lower bounds? You calculate it, and you can still say that in 95% of the time it falls between the lower bounds and the upper bounds, but not specifically this one. It gives you some confidence. So for example, if you look at this one, then based on the relative frequency in the long run and what we just discussed, I know that if I would replicate time and time again this experiment, I would know that it would in 95% it would fall between lower and upper bounds. So this experiment could be one of those 5 where it doesn't. But mostly it falls between. Does that make sense? Trying. Cool. Okay.
But
Yeah.
I have a question. What is it exactly that you can conclude based on those confidence intervals?
The conclusion that you take eventually, and we'll get there in a bit, is that you decide to reject the null hypothesis or not. So your null hypothesis would here be there's probably nothing going on. There isn't a difference in population means between these 2 groups. For example, men and women and intelligence. And if you do significance testing and you use you can visualize this through the confidence intervals, you could conclude to refute the null hypothesis and would say, well, there's probably a difference then.
Oh, okay.
Yeah.
Okay, thank you.
Okay.
Can I ask another question?
Of course.
How can you calculate the confidence intervals of an experiment who maybe is not one of the experiments that is in the confidence interval? You said something about maybe this experiment is not one of the experiments that
Yeah.
within the 95%.
I understand. Yeah.
So I don't understand how you can calculate that from that experiment then.
That's a good point. So you calculated just for this one. So going back to this one, if you calculate it, it's one of these gray bars or one of the red bars, but you don't know. So if you see this confidence interval, what it gives you is a notion that at least I'm certain that in 95% of the times it does fall between a confidence intervals or not, but not specifically this one. So yeah, it's a hard point, right? We'll continue with the example of last week. What I have here is the binomial distribution, again, as we have looked at last week, where we had thrown 10 times, and we, based on your on all of you throwing the coins, we determined what the sampling distribution would be. And there was a question in the chat that I saw where it stated, well, how do you know that it's that your population is always normally distributed? You don't. But if you create a test statistic, for example, what we do here based on the test statistic, the amount of heads, and we create a sampling distribution, then this sampling distribution is always normally distributed. And I'll touch upon that later in the course. But going from population distribution, creating a sample, and then making a sampling distribution based on the sample that you've taken will give you known probability distributions. It doesn't always have to be normally distributed. It could also be F distributed, but we'll get to that later in the course. But they're always known, exact, mathematically determined probability distributions. But we'll get to that. So what we see here is that, of course, the most frequent observation that you would have when you throw 10 times head is that you throw 5 times head. That's the expected value. And what we can also see that there are outcomes that are quite rare. It's quite rare to throw 0 if you have thrown 10 times, 0 times head, or 1 times head. It's also rare. And 9 and 10 is also rare. So, as I said last week, it's if this is the case, that even under normal circumstances, under the assumption that the null is true, under the assumption that that you have a balanced coin, it happens that you throw 0 times head, and it happens that you throw 10 times head. So what you have to take home from this is that you, based on the null distribution, you can't for certain say that something is true or the other thing is true, because you see that it happens. It is probable. So you can't say it determine indefinite, and that's a notion that you have to take into account. So if you can't determine indefinite if it's a fair coin or not, then you have to determine what the criteria is for your decision, for your conclusion to decide to denounce the null hypothesis. And that is where the Neyman-Pearson paradigm comes in. Because if I have thrown 2 times head, then the alternative distribution, well, it could be this one, but it could also be this one, or this one, or this one. And last week I said, well, we'll assume for the sake of the argument that our alternative distribution has a parameter probability of landing heads of 0.25, but it's an assumption. It could be 0.26 or 25.7431, or it could be 75% or 75.543%. I don't have a clue. I also only can observe that I've corrected my coin, but I do not know what the alternative distribution looks like. So you have to take that into consideration, and we'll go into this, and I hope you get a notion of what in that sense, what the limitations of the null hypothesis testing actually is, because we decide only to accept the null or reject the null. So if you only decide based on the null distribution, then, well, what are you saying then about the alternative? That's a hard point, a hard argument to make, but we'll get into that. So the way Neyman and Pearson have created this reasoning scheme within null hypothesis testing is to relate to relate it to logic, where as I said, you will conclude either one thing or the other based on a bunch of premises, but essentially you make conclusions. And if your conclusions is to reject the null hypothesis, or to decide to not reject the null hypothesis, to refute it, and in actuality, which we don't know, of course, the null could be true or it could be false, you have a 2x2 decision matrix like this one, where obviously you can make 2 mistakes, where it's either true in reality and you say it's not true, that's wrong, or you have 2 good decisions that you could make, namely it is not true and you say it's not true, or it is true and you say, yeah, it is true. And before we dive into the technicalities of this, intuitively it's totally logical, right? That you, if I ask you what is the the desired probability between 0 and 100% that you would like to have as a researcher, or in life in general, whatever, maybe in life, yeah. What is the desired probability for you to make a mistake? So give me an answer. What would you like to be the probability of making a mistake?
0.
0. That's a very good point. So we don't want to make mistakes, right? And what would be the probability to make a good decision? Well, we want it to be a very high probability. Now we have, of course, a problem with this 0, because actually a probability of 0, we can't calculate this. So that's a very small one. So in actuality, we can set our own tolerance on how on the mistakes that we are allowing ourselves to make. So we'll go through this whole decision table one by one to really hit the message home. But try to think of some everyday situations where the null would be true, and I would decide to reject the null. So one of the examples that if I go to the doctor and the doctor says, well, you're pregnant. That's a type 1 error, right? Because it's certainly not true. But the doctor decides to reject the null hypothesis and says, well, you're pregnant. That's a mistake. And in the other situation, if my wife, if she were pregnant with a big belly, would go to the doctor and the doctor would say, no, you're not pregnant, that would be a mistake too. So you can think about everyday situations where you can apply this decision table. Yeah, it's good to do this to get a bit of a notion of well, these types of errors that you can make and the types of correct decisions that you could make. Is this clear?
Yes.
Yeah, cool. So we're going to deep dive into the definitions of each and every one. Yeah, we'll go into this. I see the chat, the chat which talks about false positive and false negatives, and we'll go into this. But before we go into this, I think we cannot do it without having had coffee or something to drink. So we are going to have a break. We'll start at 10 again, and then we'll continue. Is that okay with you? Just cheer for coffee.
Yes.
Yeah, cool. Okay. See you at 10 again. So, I've got my coffee. I hope you do too. So before we continue, I wanted to address one point, because I'm giving this same course, not for the psychology department, but for the psychobiology department in Dutch, that's running the same week. And I have a lot more interaction with students. There are a lot more questions, and we have more conversation, and I really like the conversation. So the people that are talking to me, so kudos. But I would like to have this a bit more. So please, if you can, turn on your camera so I can see you, but engage and ask your questions, and let's have this discussion on the topics that if it's not clear, let me know, because this works, I think, better for me, but also better for you. So the pitfall of this online education is that you view it as as consumer material, right? Just like you watch Netflix, you sit back and watch the show, and it's education, and education doesn't work that way. You have to engage, you have to focus. So please try to get in that mindset. You have to sit down. It's better to sit at your desk, make notes, than sit on the couch, have your YouTube stream running on your TV. So that doesn't work very well. So I would ask you to participate, to ask questions, and go from consumer mindset to active participation. Even if you don't have questions, and you need to write your questions down if you don't want to ask them, or things that are not clear to you. So try to actively participate. Especially for yourself, to make the most out of the interaction that we're having now. And is that okay?
Yes.
Thank you. Okay. So here we go. The decision table, and as was mentioned in the chat, we will start with the first part, namely alpha, and that is indeed a type 1 error, which is a false positive. And where in psychology, psychological research, it is mostly set to 5%. It's the can you think of any situation where you would want to change this 5%?
Corona testing.
Corona testing. Why?
You probably want a higher percentage of being, a lower percentage of wrong.
Yeah, so you want, so the thing is, when it's more, when the results matter more, for the impact would be higher, then you would lower the percentage that you would have to lower the percentage of a mistake you could make, right? So corona testing is one, but I would argue that for most medicine and research where the outcome is the difference between life or death, then it would be even more crucial. So it depends on the research, and your thought process is absolutely right. If it matters more, if the consequences are higher, you want to be more critical and you want to allow for fewer errors. So if you look at the decision table, you have the columns which state the the null hypothesis is true, and the alternative hypothesis that is false. So in terms of distributions, when you're thinking about the coin experiment, which distribution holds for alpha? At what distribution must we look?
The null distribution.
Very well, that's good. So, because we assume the null to be true, then we would, if that is the assumption, and you define the probability based on that assumption, so under the assumption that the null is true, what is the probability that I would allow for my mistake? Or in our example, what do we deem rare? And we could choose 5%. And if we look at this point, the rarity, and what we're doing here is testing two-sided. So we could either, I don't know what the outcome of the coin would be. It could be skewed to landing heads, or it could be skewed to landing tails. So the rarity is at the outskirts of this distribution. And we want to determine what the 5%, if we choose a 5% for alpha, where does the the boundary, where do the boundaries end up? So as is clear to see, the rarity is at the outsides. Because we're testing two-sided, our 5% has to be 2.5% on one side and 2.5% on the other side. So if we do that, we go from outside to inside, and when we get on the left side to 2.5%, we set our boundary. So this is the red dotted vertical line is the boundary that we use if we would choose 5%. Is that the case here? I don't know if you could see it, but I'll zoom in.
No,
So what's the problem here?
it's not 2.5% yet. But if you do the two, if you draw a line after the two, then you have more than 2.5%.
Exactly. That's absolutely right. So normally you would just, especially if you would have a continuous distribution, you would just exactly see where your 5% of 2.5% area is and stop there. But because we only threw 10 times, we don't have enough precision to exactly set the boundary at that point. So in this case, we actually don't have an alpha of 5%. It's less. But if we would indeed include the 2 and therefore also the 8, then we would be way beyond 5%. So in this case, we stop here. What can we do to compensate for this? Any idea? To correct this, to make sure that we are able within a binomial distribution to more accurately set our boundaries for 5%? Anyone?
By having more flips.
Exactly, by increasing formally the sample size. So instead of throwing 10 times, you could throw 20 times and you would have more accuracy, and you could more easily determine what this percentage would be. Very good. So I'm seeing in the chat that 0.025 on both sides you can check with a t-score. You actually can't, because we'll go into that later, but a t-score is based on a continuous distribution. So it's a different probability distribution that we actually use for flipping coins. Flipping coins is a binomial distribution, so you can't go from a binomial distribution to a t-distribution. So you have to be mindful for that, because the outcome space for binomial is discrete, and for a t-value it's continuous, but we'll get to that. So the most important part that you have to take home now is that based on you choosing your alpha level, you set your boundaries. You can see the boundaries here. It's the red dotted line vertically. And now you have to translate this into the decision that you make. So the decision here for alpha is to decide to reject the null if it is true. So where do we reject the null if it is true? Can you say? Where lies our decision to reject the null?
If you throw a 0, a 1, a 9, or a 10.
Very good. Exactly. So this step goes from setting boundaries and then understanding that your decision, only your decision to say, I refute it, it's on the outside. And if you're in the inside, so if you throw 2, 3, up to 7 or 8, then your decision is not to refute the null hypothesis. Is that clear? Because that's very important, that you understand that you set boundaries and you decide something at the outside and decide something else at the inside. Is that clear?
Yes.
Yeah.
Cool. Very good, because it's very important. So it also means that if you would choose a different alpha level, your boundaries would shift, but the decision is still outside of the boundary. I decide this, and inside I decide something else. Okay, and that's fundamentally different than what Ronald Fisher thought. So they Neyman and Pearson really are now able to, even before you do your experiment, to determine the probability of making a mistake by going this route. But we're not there yet. So we're going from through the decision table, but what you have to keep in mind that we determine our threshold for our decision based on this, based on alpha. So our vertical boundaries, they're set now. We will take these boundaries to the next step. And the next is, what is the power? What is our probability of correctly rejecting the null? So we can think of this in terms of, if some alternative distribution would be true, then we could know what that probability would be. That is a problem on its own, and we'll get there in a bit. So for my example last week, I said, well, I assume the probability of landing heads would be 0.25. So if when I did that, I had a very explicit understanding and an explicit determined what the alternative distribution would look like. So if that would be the case, then I can take that and apply it to this decision table. So the power of a test, it of course is a true positive, and it's also defined in terms of 1 minus beta. And the 1 minus you will come across very often, and it's always related to the fact that if you have a probability distribution, the total probability of everything is always 100. So if you chop it up, set a boundary somewhere, then you have a probability area on one side, and the other side is always 1 minus that same probability. So you will encounter that more often. What we see in psychological research is that mostly we try to max out our power at 80%. So the probability of making this specific correct decision, we want to set at 80%. So relating this to our decision boundaries would mean that if this would have been the actual alternative distribution, then I still have the set boundaries. You can see that. These boundaries are put here based on our chosen alpha value, 5%. And my question to you now is, how much power do we have in this test? So look at this graph. Anyone?
But the alpha level is bigger than 5%, no?
No, the alpha level was actually a bit smaller than 5%, but so based on these boundaries, what is the power that we have here? How much?
About 0.23.
About 0.23. Who agrees? A show of hands. I'm looking at your screens now. Who does not agree?
Is it not 0.756?
I see that in the chat. So where does the 0.756 come from?
Because you said 1 minus beta.
Okay, but we haven't looked at the beta yet, right?
Yeah, true.
That's true.
But isn't the alpha, you can only find the alpha in the null distribution, right?
Yeah, so we're not looking at the alpha anymore. So what's happening here is, here we had our alpha, and now we're looking at the power. So it's in the column where it assumes h0 to be h null to be false. So in our example, we're now stating that, well, if h0 is false and I assume this alternative distribution to be true, then my alternative distribution would look like this. So this is the alternative distribution, the one where I assume Conrad to be out of balance and the probability of him landing heads to be 0.25. This is the probability, the binomial probability distribution of this. And my question here is, what is the amount of power that we have is if this alternative distribution would be true? One minus red bars, I see. Is there anyone that agrees? Someone that does not agree?
But 1 minus red bars would be the 0.756, right?
Okay, yeah. So let's go back to the decision. It's the power, it's this one. We decide to reject the null. That's our conclusion. Where do we decide to reject the null? Outside or inside?
Outside.
Outside. So keep that in mind. You decided to reject the null, so it's outside. So my decision is to reject the null, so that's outside. What is the probability of this being a good decision if this alternative distribution would be true?
Okay, so it's 0.244 then.
Exactly. So it's the probability of throwing 0, that is 0.056, plus the probability of throwing 1, which is this one, 0.188. So we have about, 23% probability of making, of this. If you take this decision, what is the probability of this decision being a good decision? If this specific alternative would be true, it's 24.4%. I see here by David. You would also need to add 9 and 10, but because this distribution is so skewed, those probabilities are, it doesn't happen, it's 0. So adding the red bars, the decision is to reject. So it's this this cell which relates to the alternative in this assumed alternative being true, and the decision that we take is to reject it. So we find that we find our power at the outskirts of our set boundary. Is that clear?
I have a question.
Yes.
Go ahead.
If we chose to reject the null hypothesis, that would be evidence that the alternative hypothesis were to be true, right? So that we could probably accept the alternative.
The point is that we are actually not there yet.
Oh.
The point is that in this stage, we're actually not looking at our data yet. We're not looking at how many times had I thrown. I know how many times I've thrown, I know the sample size, and based on that sample size, I could make a null distribution, and I could, in advance, say what the probability is of rejecting the null. So I set that to 5%, so I want that to be rare. And if I assume this specific alternative hypothesis, and I would reject the null based on those set boundaries, this wouldn't have a lot of power. It would only be 25%. So if I make this decision, and so let's see it from a more intuitive perspective. This distribution, this alternative distribution, looks a little bit like the null distribution, right? So it has its weights. Also, a bit from the middle. It's not at 5, but it's a bit skewed. So if I were to reject the null based on the null distribution, well, you don't have a lot of power to say, well, this alternative distribution is true, because, yeah, it looks a little bit the same. If it were even more skewed, let's say that the mass, the top would lie at 1, then I would have more power, right?
I just don't understand why you have more power outside the boundaries and not inside of it.
No, it's not as a question of more. It's a question of definition. The power is defined by the bars outside the boundaries. It's a definition thing.
Okay.
So the probability of when you reject the null, and if this were true, then this is the probability that you would make a good decision. Well, that's not that high. We would rather see a 80%.
Okay.
Do you have any idea what we again could do to make this better, to have more power?
Probably increase the sample size, because then it gets normal distribution.
Absolutely. Again, just increase the sample size, and we would see that we would gain more power from more observations of our data. And we'll look into that later on in the lecture. We're not there yet. So the thing to keep in mind is that we're not, this is still not based on the found test statistic. It's only setting our decision rules, setting our boundaries, and knowing where we decide what and what probability relates with that. Now we have, of course, a problem, because I'm assuming this alternative distribution, right? And that's actually quite arbitrary. It could be any value. So if you do an analysis in SPSS, then SPSS gives you power and gives you an indication of effect size. And that actually is not the power. Because what SPSS gives you back is the so-called post hoc power. So what we also know as the observed or the retrospective or achieved or a priori power. And it means the definition that I've shown you here. So try to read this for a second. The power of a test assuming a population effect size equal to the observed effect size in the current sample. Let that sink in for a moment. So if you read this, what in my example would be the mu, the mu of the alternative distribution in my specific case, the case of Conrad. Anyone?
0.5.
0.5 I hear. Anyone agrees? Anyone disagrees? It's my Conrad, right? The one that I hammered down and that I flattened again, and I wanted to know if he was in balance or not. And I threw 10 times and I tossed 2 times head. So what would be the alternative for the alternative distribution, the mu, for Conrad? What would be the test statistic if this is the if this is your definition of power? No? 80%. I see, David, you say 0.2. You're correct. Could you elaborate?
It's actually 1 minus 0.8.
You don't have to go that route. The thing here is that if you define the power in terms of the observed effect size, or the observed numbers of heads that I've thrown in my sample, I threw 2 times heads, so it's just 20%. So instead of having this distribution determined by a theta value of 0.25, which I assumed, according to this definition, I would have to assume, or at least SPSS gives you back, that it would be 0.2. And the effect size is the difference between your mu from your population and your mu from your alternative distribution. So that's the difference between 5 and 2. So in that sense, it would be 3. But more importantly, what is the problem with this? Why is this problematic? So you would say now, based on post hoc power, you would say mu, yeah, the population mean. It means. It's not just the mean, it's not the sample mean, it's the mean of the population. Very good that you defined that.
But how can you say, how can you say the mu of the alternative distribution? Because then that's not the population mean, right? Or is it a population mean?
Yeah, that's normally we would say the population mean, of course, but now we're talking about binomial distributions, and so actually I want to relate it not to the population mean, but to the test statistic. What is the expected value of the test statistic if the probability of landing heads would be 0.2? Well, that's 2. Throwing 2 times. So if I throw 2 times, it's reasoning the other way around. And saying if you throw 2 times, then I expect the population parameter theta for the binomial distribution to be 20%. So that's what we're doing here. And my question to you is, why is this problematic? So now you're saying, if I run a sample, I'm assuming the alternative distribution to relate to the outcome of my data.
Well, I guess it's a problem because you want to test them against each other. You want to be sure if you're going to reject the null hypothesis or accept it.
Mm-hmm.
And if you assume that the effect size is the same in the population as in the sample, you can't really make that judgment based on the post hoc power. Because you assume the effect size is the same.
Yeah, but actually your null hypothesis is that there is no effect size.
Mm-hmm.
And now you're saying when I run my sample, then I find a specific effect size. But you're doing amazing, Connor. it's in the chat. Yeah, so
Connor.
You're not Connor, okay. It's not really the point that I'm looking for.
Mm-hmm.
Is it not that one sample isn't really representative of all?
Exactly. You're doing one sample and you're saying, well, this probably is the way the alternative looks. But, well, the alternative, what would happen if we do the sample again? Would we get exactly the same results? It would be different, of course. Yeah. So this is problematic because if you define your power or your post hoc power in that way, your post hoc power will be totally dependent on your current sample. And we know that this doesn't hold for every. It will be different for every sample that you take. So what could you do to what could you do to alleviate this? So what would be the solution here?
You could repeat your 10 times throw a couple of times.
Exactly. So if you redo the experiment, if you replicate and you find a different sample test statistic, and you do it again and again, you could get all these values together, and you could estimate what the alternative mu would be. So how do we call this type of analysis?
Sampling distribution?
You would create, in essence, very good, a sampling distribution of your alternative.
Repeated measures?
I hear repeated measures. No, that's not exactly it. I'm looking for meta-analysis. So that if you run meta-analysis, you have a more thoughtful. You have more information to determine what your actual alternative distribution could look like. So for that, we need to add to all our experiments the effect size that we find. So where I told you earlier on that it's a bit problematic to only report if there's a significant result, if the p-value is lower than 0.5, 0.05, then that is a bit problematic because you're only saying I reject the null, but as we have seen that if you increase the sample size, well, everything will be significant. So adding the effect size as a measure will not only give the reader of your publications an indication how large is the effect, but it will also provide information for other researchers to do meta-analysis to get a more thorough understanding of what the alternative distribution would look like. So we have to calculate this effect size. We will do this during this course, and also we have to add this effect size in the reporting of our research results. And the effect size is determined by the difference between the mu of the null distribution and the mu of the alternative distribution. So in absolute values, what I've already said it, but just to see if you picked it up. So in absolute values, what would be the effect size if in my coin experiment?
.3.
I hear 0.3, and I see Evelijn saying that it's 3. So I asked for the absolute value, so it's not a probability value. So I've thrown 2 times head, and under the definition of post hoc power, and assuming that this is the population parameter, then I have thrown 2 times head. The mu from the null distribution, our expected value in the null distribution is 5. So the difference between these two, the difference between the tops of this distribution, the difference between this top and this one, that difference is 1, 2, 3. So that makes So that makes the effect size in this, the absolute effect size in this sample.
You may
But, I'm sorry. Is the effect size about the difference between like the null hypothesis and stuff, but in the theoretical way, or is it this actually about a sample you have taken and then the difference of the distribution?
Yeah, so we defined our post hoc power in terms of the sample that I took. So what I was saying, I see in the chat that I didn't show the slides. The effect size is the difference between this top that we have here on the null distribution and the distribution for the alternative, the top of the alternative distribution based on the data. So if I assume my 2 times that I've thrown head to be the population parameter, so it's 20%, then I think it also would be the top. So it would be the difference between this top and the top I showed you before.
Okay, thank you.
Yeah, and it's the absolute difference. So and that is a bit of a problem because if you report absolute differences, then it's hard to compare because well, if in my experiment I've thrown heads 10 times and somebody else does the same kind of experiment but with 15 with a sample size of 15, then I can't compare these two. So it's important, and this is what's happening in effect size measures, is that the effect size measure gets standardized, and there are different kinds of standardizations, and you could recalculate all kinds of different effect size measures into each other, but you have to standardize. So if you look at this one, we see the effect size, for example, between this distance and that one, and for the other one we see it here and there. And my question to you is, which effect size is bigger? Is it sample A or is it sample B? Who says sample A? Who says B? A, B, 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 yeah, A. Who has a different opinion about
They're
the
the
samples?
same.
Exactly. They're exactly the same. And that's the reason, and I want to make this point, that if you standardize your effect sizes, and the way we do this here is by calculating Cohen's d, it's subtracting the differences and dividing by the standard deviation that we have. So if we do this, we will standardize the effect size that we found, and for this example, it would be the same for both. So it's important to take notice of the standardization of effect size to be able to compare results. And you can't see that they're the same. You can only you can see that they're the same if you calculate an effect size value which standardizes it by standardizing relative to the spread, to the variance that there is within this sample. And then if I plot the results for this one and I plot the results for this one, group A and B are exactly the same. Okay, we're still not there. We have to look at this poor thing because it's the only one that doesn't have a name. We had alpha, we had beta, we had power, but this one we call 1 minus alpha. And it is the correctly accepting the null hypothesis. It's also called the true negative. And if I go to the next slide, I will show the distribution. Which distribution is this one based on? Anyone?
Null hypothesis.
It's the null distribution because it's in the column where you assume the null to be true. And your decision is to decide not to reject the null based on the same alpha that we've chosen earlier. We've chosen our alpha of 0.5 of 5%. So if we go to the next slide, what it will look like the normal distribution, and where is the area for this probability?
In between the boundaries. You gotta add all the probabilities.
Yeah, in between the boundaries. So that's absolutely correct. So, and that's also very intuitively very clear, right? So if the null hypothesis actually is true, and I decide to not reject it, the null, then I do so when I between 2 and 8. Well, the mass of the distribution is in between there, so this probability is very high, of course. Does that make sense?
Yes. Yes.
Cool. So again, the decision to reject the null is outside of the boundaries, and the decision to accept the null is between the boundaries. Now for the final one, the beta. It's incorrectly accepting the null. We call this a type 2 error. The mnemonic, by the way, for type 1 and type 2 errors is the relation between type 1 and type 2, alpha, beta, A, B, 1, 2. So you have a mnemonic there to better remember the type 1 and type 2 errors, which goes where. And we want also this is a wrong decision again, and we also want this wrong decision to be low. We can set it to 20% mostly, and that's related, of course, to the power of our test. So what we find here is our decision to reject the null is outside, but here we decide, because it's this cell, to not reject the null. So it's the area is inside, and the probability distribution in this case is the alternative distribution. And we find it in between the boundaries again. So it's not 20%, it's a very high probability. So for this alternative distribution, we could again increase the sample size to have to decrease this this error rate. I'm looking at the chat, by the way. So the last one is the beta. So the type. Is that clear? So you have the outside, it's decision to reject the null. The inside is the decision to not reject the null. Related to the alternative distribution, you could get your power if you decide to reject the null, and you will get your beta if you decide not to reject the null. Yeah? Okay.
So I have a question. You
Go
use
ahead.
the same criteria as the null hypothesis on your alternative distribution?
You
or
d-
I mean,
yeah.
the same.
Yes.
Yeah.
Yes, you decide your criteria based only on alpha, only on your type 1 error. So you decide what your type 1 error is. You decide what the type 1 error you allow yourself. So I want to be wrong in only 5% of the time for this mistake, and the mistake being rejecting the null when it's actually true. And there you set your boundaries.
Okay.
Period.
Okay.
And that transfers over to alternative distributions that you could have, where you, if you know what the boundary is, and you have a specific alternative distribution, you could point out what the power is. What is the probability of this being a good decision if this alternative distribution for would be true.
Okay.
Yeah.
Yes, thank you.
So this one puts them both together. So here you see in green the the null distribution, and in orange you see the alternative distribution. We've applied the same threshold based on our alpha level. And let's see, I could ask you, what is the power here? And I want a value. So this one is a little bit different. So I chose a different alternative distribution, slightly different, but tell me what the power is here in a number. And these are exam questions that you could ask, because I want you to fundamentally know what alpha is. I want you to fundamentally know what the power is, what makes the thresholds. So based on this, how much power do we have?
0.36.
Yeah. I'm seeing 0.36, 0.37 coming by. And why?
Because it's outside the boundaries of the alternative distribution.
So it's outside the boundaries, that is correct. And because you're looking at the power, we're talking about this alternative distribution. And that means that you would have to add up what?
0, 1, 9, and 10.
Yeah. So the height of the bars, the probabilities of those areas for values 0, 1, 9, and 10. And that exactly is about 0.11 plus 0.27, and 9 and 10 are well, nothing. I'll zoom into this, but this is flat. That's good. That's good. Very good. So based on these kinds of graph, I could ask different questions on where to set the boundary based on a certain amount of alpha, and I could change the alternative distribution. You could also change the amount of heads that you have thrown. So we have 10 times here, but if I increase the sample size, this would look different. So very good. So what you have to realize now, that everything we've done up till now is only based on our sample size. So it has up until now nothing to do with the actual results of our data. It's only based on our sample size that we can set up all the premises that need to be set up for the Neyman-Pearson paradigm to hold. So we have set up the null distribution. We have chosen some alternative distribution, which in actuality we don't have, of course, huh? And we decide only to reject the null, but we don't know what the alternative distribution is. We could use our effect size to make a guesstimate on what it would be, but we're not really sure. But it's not based on the data. So the next step is to find out how this relates to our p-value. And when we go to the next slide, you can see that we define the p-value as the conditional probability of the found test statistic, or more extreme, assuming that the null hypothesis is true. And this is a bit double, because assuming the null hypothesis is true actually means the same as a conditional probability. It's the probability of finding this test statistic or more extreme, and in our case it's finding 2 times head or more extreme to the outskirts, assuming that the null hypothesis is true. Where we reject the null hypothesis if the p-value is lower or equal to alpha. So in the next slide I'm going to show you the distribution and which part it is, but what do you think that it will look like? Which distribution is it?
The alternative distribution.
Who agrees? Who disagrees?
I think it's the null hypothesis, the null distribution, because you look whether you assume it's true, so you look at that one.
That's what the definition is stating right? It's saying assuming the null distribution, the null hypothesis is true. And if you assume the null hypothesis to be true, then you would look at the null distribution. And the area, or the amounts the bars, which bars are we going to look at? Which ones are going to be colored? I'm seeing within the bounds.
If you look where the p-value is, if it's within or if it's outside, right?
Yes, okay. So now you are relating, and not just, but I seeing it happen in the chat also. You're relating the p-value as a position on the x-axis, and the p-value is the probability. So our test statistic, I threw 2 times head, that is absolutely related to the x-axis. So I can point at 2 times head. But if I want to define that in terms of probability of finding this test statistic or more extreme, then I have to look at all the other more extreme values as also belonging to the probability. So if I look at this, I've put in the boundaries still from our chosen alpha, and the p-value here, and I'm still testing two-sided, is the probability of the found test statistic 2 or more extreme. Well, what is more extreme than 2? It's going to the outskirts. That's more extreme. And what is the probability? So the probability is 0.044 plus 0.01 plus 0.001, and the same, because we're testing two-sided, the same on the other side. So this is our p-value. So our p-value is, so what is it? 44, 45, let's say let's say 9%. So the area, the probabilities of these bars added together, 0, 1, 2, 8, 9, and 10, that is our p-value. 11, I see. Thanks for calculating that for me. And that's higher than our threshold, right? That's higher than the 5% we would allow ourselves to make a mistake. And it's saying exactly the same, or the result of this is exactly the same as just realizing that, well, I've thrown 2 times head and it's inside the boundary, so my decision is to reject the null, to accept the null hypothesis. And that's the same as saying, well, the area under the curve, or in this case under the bars, outside of the thresholds is a smaller area than the area of the found test statistic or more extreme. So it's concluding exactly the same. Yeah. Is that clear?
Can I ask a question?
Yeah?
You go.
Oh, thank you. So I don't really get how you decided to paint those bars blue. I get the line, and I get the 5%, but I don't get why the 2 is in blue. I don't get the criteria.
Because the p-value is defined as a probability. The p-value is not defined as the test statistic. It's not just 2. No, the p-value is what is the probability of 2.
Yeah.
And the probability of 2 exactly is 0.044. But it's not just, the definition of the p-value is not just the probability of 2. No, it's the probability of 2 or more extreme, and that's a definition question, right? It's the probability of 2 or more extreme to the outskirts, so we also add the probabilities of 0, 1, and because we are now also testing two-sided, we would also need to look at the 8, 9, and 10. It's defined in terms of probability, so that's why you're looking at coloring the bars blue.
But shouldn't the alpha level, the red lines, then move behind the 2 and the 8?
Shouldn't the question if the red line now shouldn't move based on our p-value?
Yeah.
We determined what our threshold was, right? We said that we put our threshold at 5%. So that is our criteria.
Yeah.
We know it from in advance. We set it there to as a decision rule to say if we find data which is on one side or the other, we decide to reject or we decide not to reject. So the criteria stays put.
Okay. Yeah.
Yeah?
Yeah.
Okay.
Thank you.
So I know that this is a hard one, but what's not hard, I hope, is that obviously 2 is inside of the thresholds, right?
Yes.
Yeah, okay. And we're going from looking at this 2 to looking at the probability of 2 or more extreme. And the probability is just the height of these bars. So what I'm saying, 11% is higher than 5% is the same as saying, well, 2 is higher than the threshold that we have set for ourselves. And it's not much harder than that.
But how did you calculate the p-value here now?
Okay.
How did you get to that number?
I got to that number because I had thrown 2, and I've looked at what is the probability of throwing 2. This is 0.044, but the definition of the p-value was this test statistic or more extreme. So I also have to add 0.01, and I also have to add 0.001, and because we're testing two-sided, I also have to look at the other side, which, because it's symmetrical, is the same. So adding the height of these bars, the blue bars, gives us the p-value.
So you already have data.
Because I threw.
Okay,
I threw two. I threw 2 times with Konrad's coin.
So it's based on your alternative distribution you showed here.
No, it's not based on my alternative distribution. It's based on my data that I found. It's based on the test statistic from the coin that I flipped. I flipped, and I had 2 times heads. That is my test statistics. Assuming the null distribution, this is the probability that I get for throwing 2 times. You could also think about what would be the probability of throwing 2 times heads if you assume some other distribution. Yeah, well, that would be different, but that's not the definition of the p-value. The definition of the p-value is the probability of this test statistic assuming the null to be true. So if I assume the null to be true, like this, then what is the probability of finding 2 or more extreme?
Wait, so the question would be worded in that way. So they would say, given the null distribution, and given that you got 2 heads, for example, what is the p-value?
Exactly.
Okay.
So for example, if I would have thrown 4 times heads, what would have been the p-value in this case?
Sorry, could you repeat that?
So if I would have thrown 4 times head, for example, what would have been the p-value?
Would that have then been the probability of throwing 4 or more extremes? So you'd have to color in 0, 1, 2, 3, 4, leave out 5, and then do 6, 7, 8, 9, 10.
Exactly. And in terms of what the exact value is, would be, then you would have to look at what is the probability of this one, 4 plus this one plus the one below.
More easily 1 minus the probability of throwing 5.
This one, this one, this one, this one, this, and on both sides, assuming that you're testing two-sided. If you test one-sided, you're only looking at one side of the distribution. I know this is hard stuff. So you need to work on this and try for yourself. And for that, I have created test statistics. I've created this code. You can run this code in R. You don't have to know exactly what it all means. But if you run it, you will get the following graph. And that's this one. This is the decision scheme that we had. Assuming the null distribution to be true, assuming it to be false, and filling in a specific alternative distribution, and the rejecting the null or accepting the null, and it's coloring in the regions that you would have for this one. So if you have this code, you could also say, well, what would be the effect if I would increase the sample size, because we've talked about this a lot. So for example, if I would say instead of throwing 10 times, I would like to throw 30 times, what would this look like? Oh, here we go. Yeah. Something went wrong here, but you see you have more observations. You can be more accurate with determining where your alpha level cuts off, and you also see that if you have more observations and your alternative distribution is defined as 0.2 or 0.25, I don't remember, then you immediately have much more power than you would normally have. You have to go and play with this. Just fill in some different numbers, fill in some different values not just for the sample size, but also try to do it for the for different values of the alternative distribution. Okay.
Does it matter if your alternative distribution is one-sided or two-sided? Like,
your alternative distribution is not one-sided or two-sided. It does matter in your decision if you decide to test one-sided or two-sided, because in that case you have the 5% only on one side and not on the other side. So it would definitely matter on which areas will be read. Yeah.
Would it matter for the power table, the power distribution?
Yes, because your cutoff point would shift and would only be on one side.
Oh, okay.
Yeah. So go play with this. I had the reasoning scheme and the ARP psychologist website also. Just try to look at this for yourself, because here you can play with some parameters. If you want to solve for power, you could see what the effect would be of increasing the sample size when your alpha level stays the same. So these are just some handy tools that you could use to get a bit more insight on this. Okay, I'm stopping. Is that okay for you? This was a hard one, right? We'll go into this much more during the whole course, and eventually this will land. So I have confidence in you. Thanks for being here, and good luck with the weekly assignment again. And I hope to see you all next week. Bye.
Bye.
Thank you.
Bye.
Bye. Bye. Thank you.
You're welcome.
Bye. Bye. Thank you.